these kind of features, not all the older forms of machine learning. They used to use meaningful features about words. For example, what is its co-location with other words? And then is it a noun? Is it a preposition? It's part of speech and things like that. The current brand of machine learning does not use that. It uses more signal processing type measurements for words that are just numeric representations that don't mean anything to a person inherently. So interpretability has become very important now because the features don't mean anything to a person, but the features work. Why they work? Through previous classes, you have been exposed to a lot of models. Uh, and what it boils down to, and I'm simplifying it greatly, is all of those models have different capacity to approximate a function. And the true underlying function, the way it operates in mapping inputs to outputs, doesn't need to make sense to a human being, right? It just needs to be correct. So you have raw measurements and you have a function that has very high approximation capability. And if it maps to the correct output, so if it reliably predicts y is equal to 1 or 0, you're satisfied because your function did the right thing. Is that function meaningful to a human? That's a different question. Okay. So now let's think about the types of functions you have been exposed to so far, types of machine learning models. So in the first part of this box, you see a example of a positive linear correlation. Logistic regression, for example, is a function that is a model that falls into this category. You have a set of features, you have a linear combination of those features, you add a bias, and the link function is the log odds, right, to convert it into a probability. Um, Another method that you have studied that falls into the first category is a support vector machine. You have a linear function of features plus a bias, and the link function is the sign function, right? You don't necessarily need to interpret that as a probability because the sign function is +1 or -1, but that's also an example of the first type. What about the second type? It is still a positive linear correlation. The only difference between the first type and the second type is that the feature vector is now mapped to a set of higher order features. So what do I mean by that? In SVM, you have studied a kernel map. So a kernel map computes dot products between features mapped to higher dimensional spaces. So the kernel is, you can think of as first mapping features to high dimensional spaces, then taking a dot product between a pair of points once those pair of points have been mapped to high dimensional spaces. The kernel trick allows you to compute that dot product without explicitly mapping the features to uh, high dimensional spaces. But essentially, under the hood, what is going on in a kernel support vector machine is a linear function is being learned where x is replaced with a high dimensional mapping of x. So that's an example of the second type of function that you see here. Another example of the second type of function that you see here is a neural network. I know traditionally neural networks are not typically thought of as linear models, but they actually are because um, you take an input vector x, you transform it to through a series of activations, nonlinear activations and linear combinations, to another feature vector phi of x, which is you can think of as the final layer of the neural network, and then it's a linear combination. So the higher order of x in this second equation you can replace with the neural network up to the final layer, and it's still a linear correlation, right? So what about decision trees? Are decision trees linear models? So here in this, you can see a two-level decision tree with two variables. And you can write this out algebraically as, and let's say x1 and x2 are Boolean variables, right? So you can write this out algebraically as x1 being true and x2 being true, or x1 being true and x2 being false. x1 being false and x2 being true, and x1 being false and x2 being false, right? So yeah, it is a linear model, right? Except it's not parameterized. You don't see any thetas. So it's a non-parametric linear model. So uh, now the question we need to ask ourselves. So Dr. Gore, at the start of the class, mentioned that decision trees are interpretable, right? So let's think about that issue a little more deeply now. So the first condition for interpretability is that all linear models are not necessarily interpretable. The tractable linear models are, it's necessary for linear models to be tractable to be interpretable. So what do I mean by that? So when a feature vector is given to a traditional machine learning model today, like I said, it has very high number of dimensions, like 300, 700, and so on for word vectors, for example. So for it to really be interpretable, you'll have to be able to track a small number of linear relationships between those 300 dimensions. Otherwise, even if you have a linear function, it's not really interpretable, right? So uh, this slide is showing examples of interpretable linear functions, linear correlations. So here, this is what I meant when I said at the start of the class that we want to decouple the notion of interpretability from model choice. Your model choice could be a decision tree, it could be a neural network, and it could be a linear model. But all of them can be interpretable or not interpretable, right? So here you see examples of interpretable versions of each of these three, because you can track the variables x1, x2, and how they influence the outcome y, right? So now moving on to the next slide. This is a picture of a tree I found on LinkedIn. So this is the tree as we understand it in computer science, where the root is at the top. So if I asked you to trace a path from the root to the leaf on this tree, you wouldn't be able to do it easily, right? So a tree that is this large is not tractable. Pay attention to the word tractable when I say you cannot track easily a path from the root to the leaf. So the model, if it is a decision tree, it does not automatically mean that it is interpretable, right? So similarly, if you have a neural network with several hidden layers with multiple layers of activation, you can't really track what is going on in the neural network. Okay. So with that, what should you do about it? So first, we need to understand that there is a trade-off. So the more interpretable your model is, the less approximation capability it has. So going back a few slides, these models are interpretable, but uh, if your function is really complex, you will need more layers of a neural network. You will need more branches to your tree, right, to approximate it. So by their very nature, these two objectives are at odds with each other. Interpretability is always at odds with approximation capability, right? So what do we do about it? So now, until this point, we talked about what is an interpretable model, but we didn't talk about it is interpretable to who. So remember the first example I gave. If you are trying to explain the concept of a cryptocurrency to an audience, if it is a technical audience, you can use words like blockchain and decentralization and computational mining and cryptography. But if it is to my grandmother, it'll have to be, it's like the new age gold, right? And she'll understand everything about it just by saying that. So social context is very important, uh, among many other things. So when we are talking about human interpretability, now we are uh, we'll have to think about variables that are slightly outside of the realm of machine learning, right? Things that are interpretable to machine learning developers, right, is mostly things that are mathematically tractable, but those mathematically tractable objects don't necessarily need to be interpretable to the humans that use these machines, right? So human interpretability has a layer on top of mathematically tractable models. And what is that layer? The small set of linear relationships that you need to track, those linear relationships need to mean something to a human being, right? So as an example, here I have a model that is trying to explain um, the health of a person, right, to a clinician. Now, I can take that neural network on the left hand side. It's a tractable neural network, right? It has only few layers. You can see exactly input to output what is going on. But those last two nodes, do they mean anything to this person? We don't know, right? So first thing to do is those last two nodes, we'll have to map them to a set of features that the human cares about, right? And then use some method. We'll get into the details of the method later. I've been told that some of you are familiar with Lime, but we'll get to the details later. You use some method to then map those interpretable, human understandable features to some kind of model that the human can make sense of. Now, so to repeat, you take the model, you map the model's outcomes to a set of features that the human cares about, and then you learn a separate surrogate model that takes those human explainable features and predicts the outcome, right? So now the human can start to understand what is going on in your original model by using the surrogate model, right? So uh, another point people get confused with when they're starting on this topic is I've already said this before, but I'm just going to repeat again that when you have a set of features, no matter what function you have, if you zoom in close enough, it will always be a linear model. So the notion that all linear models are interpretable is just wrong, right? It does need to be tractable. So, uh, so what is our issue here? The issue is that we lose approximation power if we keep our model small and interpretable. So we don't want to do that. We want to retain approximation power, but then solve an alignment problem, which is align the model components of the approximation model with a set of features that a human can understand, right? Lime is one way to align it. Here I'm showing you a picture of another way to align it. You could use knowledge graphs. So an example of a knowledge graph is, for example, Wikipedia. Uh, Wikipedia or a textbook on clinical knowledge, right? So what you see here in this slide is a textbook on clinical knowledge. So the text that you see really struggling with all of that stuff, um, the highlights in that text comes from simply highlighting the words that cause high activation in your neural network, the thing on top. But now those highlights, how do you interpret those highlights, right? All I know about them is that they caused high activation in the neural network, right? So the additional knowledge that I have from the textbooks lets me interpret them. What kind of classes are those highlights related to? Health related classes. What kind of definition does it fit that you see on the top right corner, right? So this is one example of how you might align the approximation of a function features or components, which is activations and model parameters, with things that you can make sense of, right? So now coming back to Lime, exactly what does Lime do? So Lime, the first thing Lime requires is a set of features that is decided by the human beforehand. So the human tells you when you're trying to provide an interpretation through Lime to the human that they want to know specifically about the sneeze, weight, headache, no fatigue, and age, right? But that's not enough. So remember, the pipeline is that you have your approximation model, you get these features from the human. Now you need to construct a surrogate model, right? So the human is not going to tell you how to construct the surrogate model. So the properties of that surrogate model is supposed to be that it needs to be tractable and linear, right? For it to be interpretable to the human. So what are such models? So LIME stands for locally interpretable model agnostic explanations, right? So going back to this picture, you could construct any model, but now the difference is the x1 to xn are features that the person understands. And now when you talk about local linearity, right, it makes more sense because it's locally linear with features that the person understands. That is the concept that LIME exploits. No matter what function you have, when you zoom in close enough, it's a linear function. But it only makes sense to a human if the feature space is something that the humans can make sense of. So LIME exploits that feature. It gets the feature space that makes sense to humans, and then just lets math do the rest, right? It's a mathematical certainty that any function you learn as a function of these features given by the human, if you zoom in close enough, it will always be interpretable, right? So that's the picture here, the magnifying glass. You zoom in, and then you can be sure that a linear relationship holds between these features once you zoom in enough, right? So that's what I mean by first order geometry. First order geometry means the linear approximation of a function around a particular data instance. So uh, slightly more advanced technique. Uh, this is a technique called shapely values. So it is inspired by game theory. In game theory, when you have multiple players playing a game, you can measure the contributions of each player towards playing that game um, in a specific way. And that specific way was defined by a person named Shapley. What is that specific way? It is the same concept as line, but it uses higher order geometry. So going back to this picture, if I was at this point, the zoomed in point, if I move a little bit away from it, I can be sure that a linear relationship holds. But if I move farther away from it, I would need to assume that here in this picture, a quadratic relationship holds, right? But if I move too far away from it, then higher order nonlinear relationships hold, right? You would need more than a quadratic term to faithfully approximate points that are quite a bit far away from where you are. So Shapley values uses this notion. It's a natural extension of line where the approximation is immune to straying from the local neighborhood of that point. But then once again, uh, you have the disadvantage that if you start computing quadratic and higher order terms, it's more expensive than computing linear terms. So yeah, the correct choice of model to use depends on the use case. Is for your use case, is it not that computationally intensive to calculate higher order terms? If so, then go ahead with Shapley interpretations. Otherwise, line, right? Okay. So now, uh, revisiting the issue of using external knowledge to guide your interpretability, why would you need to do that, right? When you have Lyman Sharp. Uh, the reason for that is, once again, this picture is important, is that Lyman and Sharp depend on the mathematical geometry, right? You go a little bit away from your zoomed in point, linear relationships hold. You go far away from your zoomed in point, then higher order relationships hold. But what if you don't, you have no idea the surface of this manifold, right? So you have no clue as to how to reliably estimate the geometry, right? That influences your how X correlates with Y. In that case, Lyme and Sharp it can only give you estimates with poor outcomes, because the geometry is not something that even makes sense to humans. So for an example, as an example, I'll say that let's say I'm asking you what is the difference between two probability distributions, right? So distance between two probability distributions is a weird notion, right? Distance between 2 points is, you can think of naturally. Difference between two probability distributions, you might have heard about KL divergence and things like that. But when you go to more abstract objects like graphs to represent a concept, distance between two graphs or probability distributions over graphs, right? As you get more abstract in the structures that define your data, it's hard to interpret any realistic geometry that applies in the underlying space, right? In that case, you would just like to use the information already present in the knowledge graph. So for example, um, if I map the neural network features to the concepts in the knowledge graph, like you see here, right? All I need to know is that for two sets of inputs, the same concepts are applied in the knowledge graph, right? So it's like the kernel trick, but the kernel trick requires the kernel trick. I'm not sure how detailed you guys went into the math, but the kernel trick relies on Hilbert spaces. It relies on dot product spaces. So that means it relies on the geometry being nice and Euclidean, right? So the knowledge graph, in some sense, provides the kernel trick in non-Euclidean spaces. So in structures where distances are no longer symmetric, in spaces where distances are no longer symmetric, and it doesn't, there's no intuitive meaning to the geometry, underlying geometry, right? So the dot product essentially means that I have an example, I mapped it to my knowledge how, these are the concepts in my knowledge graph that apply to this point, and a second point, a separate set of concepts apply. And if those set of concepts are similar for both points, then their dot product is high, quote unquote dot product. It's not an actual dot product in the mathematical sense, but it is analogous to the kernel trick in geometries where you don't know what is going on, right? So that is the mathematical side advantages of using knowledge to induce interpretability in your models. But the most significant advantage is that these knowledge structures are created by humans. Wikipedia, for example, is edited by humans. These textbooks are written by humans. So when you're trying to solve human interpretability, this is the gold standard. If you use a structure that humans have created themselves to explain to themselves what is going on, and if your machine learning model can map to those concepts, then you have hit the jackpot, right? So my research at the AI Institute focuses on this. And there are a lot of complexities that come with trying to model interpretable phenomena like this, but I'm just giving the high level idea. So in summary, knowledge encodes human interpretable features along with human interpretable geometry. Human interpretable geometry is a word I've just coined, right? It does not have any intuitive meaning other than the fact that it has an intuitive interpretation for why two objects are similar, because they map to similar human interpretable concepts. And that's it. You don't need to think about the underlying geometry, right? Okay, so with that, I'll pause and take questions.
Any questions? Yeah, no one has any major question, I guess. So you can proceed, Kaushik.
Okay, so that was all the slides I had for today. What I can continue with is uh, explaining a little bit more about the math behind LimeShap, so that you fully see what I'm talking about. How much time do we have?
We have 20 minutes.
Okay, so and then Manas, you said if you have 15 minutes left, you wanted to discuss a few things.
Yeah.
Okay.
So if you want to uh, pause, so if you can take 10 more minutes,
Okay.
and then I can. Um,
Okay. So uh, I'm going to write here a summary of what I talked about in this class, which is first, if you have a model that maps inputs to outputs, right? Uh, is this model interpretable or not is the question. The second question is this relationship interpretable as a whole, right? And interpretability as a phenomena does not depend on the model, so it is model agnostic. It does not depend on the features, right? It is feature agnostic as well. Really, what it depends on is who are you explaining to, right? So the human that will use this system, right? So uh, we started with linear models. So linear models are nice if you have good features, right? If you don't have good features, then again they don't mean anything to a human being, right? And then if you have a large number of features that are raw measurements, like a signal from an audio or word vectors, even if you have a linear model, that relationship doesn't convey anything, right? So the same applies with a decision tree. Uh, a decision tree that is many paths from root to leaf, you cannot say much about what is the function it has learned, right? And then also for a neural network, it gets a bad reputation because neural networks are supposed to be highly nonlinear, deep functions that are not interpretable. But neural networks by themselves, there's nothing about it that says it needs to be deep, right? It could be a shallow neural network with two layers with less width, and it would then be interpretable, right? But neural networks are popular because they're universal approximators. They can approximate any relationship from X to Y. So the question for us now is how do we leverage that approximation power and at the same time explain the relationship to a human? So uh, first thing is we get a set of features that the humans care about, and then create a surrogate model M2 that maps F1, F2, and the pair x comma y, where y is predicted using M1. I mean, just M in this figure, right? To set of interpretations that the humans can understand, right? This is our task. We get this from the human. We build this surrogate model that is interpretable, right? Uh, there is no fault of the original model. All it's supposed to do is have infinite approximation capabilities, right? Because the true relationships that hold in the real world uh, and the way that it maps from real world measurements to what we see uh, don't need to follow any human interpretable process, right? So we should not, the idea is that we should not interfere with that, right? But if we want an explanation for it, then we create a surrogate model that explains to us the outcomes that we see in the real world, right? So now how do we do that? We can use Lime. So we can say with these features, I have a point x1, I have a point x2, and the distance between these two is small enough that I could draw a line connecting x1 and x2. I mean, I could draw a line connecting x1 and x2 such that the output y of x1 would be equal to uh, the output y of x2. This is the assumption in line. If this criteria holds, then x1 and x2 are both explainable using features f1 and f2. In SHAP, the criteria that needs to hold is I need to be able to draw a curve, whatever that curve looks like, from x1 to x2, such that y of x1 equal to x2. And last thing that I discussed here is that the third variety, which is external knowledge induced interpretations, right? So between x1 and x2, in the third case, there needs to be a connection, right? So in when you know what the underlying geometry looks like, you can define that connection to be a linear connection or non-linear connection. But when you don't know what the underlying geometry looks like, you can define the connection to be something as simple as the concepts that map to x1 in a knowledge graph and the concepts that map to x2 in a knowledge graph are the same concepts, right? That would lead to y of x1 being equal to y of x2. And the advantages with this approach is that it does not depend on the underlying geometry, but the caveat is that it has to depend on high quality knowledge that tells you that concepts that these map to are similar. But the reality is that high quality knowledge is available in abundance today. Human curated high quality knowledge for some domains. For domains where it is not available, Lime and Shep may be better suited, right? But for domains like clinical applications or you will need to use probably some form of external knowledge so that the humans can trust your system. Contrast that with a domain like autonomous driving, right? In autonomous driving, there is no real meaning to why did your car drive off the cliff, right? Uh, and your explanation can't be that because it is not trained to be sensible, right? So these are very vague. In the clinical domain, when you use knowledge to interpret something, it has very explicit formal definition, so the interpretation has no vagueness about it. But in autonomous driving, you might be better off with an approach like Lime or SHAP, which says that there's this mathematical relationship between few human engineered features, and that's why your car drove off the cliff. For example, the position and velocity of the car at this point relative to some frame of reference was XYZ. So that's why it drove off the cliff, right? I hope that makes sense. I'll stop with that.
Okay. Any questions? Anyone who is using Lime or SHAP probably might be interested, or who is even starting to looking into interpretable machine learning as a part of the project. So I have a question. So do you think, Kaushik, that using SHAP, can I make, based on your presentation, can I infer that SHAP is more neural network centric and Lime is more like simple machine learning models?
Could you elaborate on what is neural network centric?
For example, let's say neural network has a very high level, high dimensionality geometry, right? So there you are trying to learn over a very complex set of features spanning around 300 dimensions. Whereas on machine learning, we are working with 200, like 200 is a very huge number, but you can say that around 10 to 20 features. So do you think that having 10 to 20 features seems to be more appropriate for Lime, and 300 like features are more appropriate for SHAP, to explain?
Okay, so the original features that you start with, which is 10 or 200, okay, the important thing before deciding to use Lime or SHAP is if those features are important to the use case. So the when I said that we need to track a small set of features from the initial 10 or 200 that makes sense to a human. The choice of Lime or SHAP will depend on how small that set is.
Okay.
So if we have decided that 4 out of those 200 make sense to a human, Lime is good. If we decide that 20 out of those 200 are good for a human, then SHAP is good. So in the answer to your question, I suppose would be in when you have high dimensional geometry and complex relationships, SHAP is definitely better than Line. But I'm trying to make also the distinction that it does not depend on your original set of input features, but more on the features that make sense to a human.
I see. And if I want to put it, let me take on some of the projects that I'm aware of in the class. Suppose that you are talking about uh, let me talk about, I think the one of the list that I have is, yeah. So if I talk about a paper on, let's say, which a project which is, I think, which Drew and his team is working on, for instance, is about uh, malware detection or malware analysis from online URLs. So they are looking at the URL data and they are looking at the URL content, right? So URL data is more like limited set of features, whereas URL content is a high dimensional features, right? So in order to explain that whether a site is legitimate or not, right? Would you think that the model should follow line to explain, interpret the model behavior, or SHAP to be a more appropriate in understanding model behavior? Because I think when these guys move into the content space, that is where the embeddings comes into the picture, right? In my opinion. So yeah.
So from what we saw in the presentation, right? The difference between Lime and SHAP is strictly better as a interpretation technique than Lime, provided you can compute it interactively. So definitely for use case like you just mentioned, where word vectors are involved in content description and discrete set of features are involved in URL description, there's a combination, there's a high dimensional feature set. So if you want to compute SHAP, you would probably run into overflow issues.
Okay, I
So
see.
yeah.
Okay. And one more thing. Now, suppose there is one more project which uses end-to-end self-driving cars, and the project that it does is the following: it tries to estimate, the model tries to estimate how much, what is the degree by which the steering wheel should be tilted or should be rotated, based on the let's say there is a point at the traffic light, and there might be some construction. So based on the construction, the turning angle will change, right? And without the construction, the situation will be different. Now, if you are training a model that can estimate that kind of a situation based on the images, now taking the images and you want to interpret whether the model is functioning correct or wrong, that's the task of interpretable machine learning, right? So, would you go for a SHAP based approach or a Lime, or or if you have anything in your mind that would be a more better interpretable structure than Lime and SHAP?
Okay, that is a very interesting example. So here, you gave some examples of objects of interest when deciding whether to steer or not, right? And the set of objects of interest was not very large. It was the sign ahead of you and limited scope of objects that are present around you, right? So the relationships between your car and the objects that you see around you are possibly small enough that you can model it using SHAP, and then use that to explain to someone why you turned your steering wheel. But when you're doing actual control of turning the steering wheel automatically, that requires really fine-grained relationship modeling, probably also with respect to objects that are not of interest to you. So the original neural network that had high approximation capability and was trained to control the driving of the car should probably handle the actual steering. But the explanation, I suppose, could be handled by a sharp module on top of that that takes as input the objects of interest that you specified, and the output from that original neural network that does the control,
I
and then
see.
explains the relationships.
Okay.
Yeah.
Okay. And NVIDIA doesn't do that right now, right? They don't have any interpretable machine learning model in place.
No, and but the reason for that is again the knowledge component in autonomous driving becomes important. So when, like Dr. God just said, the images in the scene can only tell you so much. So for example, if you see a ball, right, do you stop or not? Right? If the ball is of no consequence and you're on a highway, you should not stop, right? Knock it out the way. Otherwise, people behind you will crash, right? But what if the ball is being followed by a child? It's not present in the image, that information, right? So then you have to stop or not. This is some ethical dilemma, whatever it is. But the reasons for stopping or steering a particular way is not entirely contained in the image. So explanation modules in autonomous driving is an area of open research because of various factors.
Okay. And Kaushik, do you think GradCam is an interpretable model?
I am not.
So GradCam is basically a model that I was working with I think Saqib and his team. And what it says that it's a heat map representation,
Okay.
right? So you have an image and you have a model weights. And what you're trying to do is that you're putting your model's images onto that heat map as an illustration that the heat map signifies the weights of your model.
Mm.
And where it is highlighting densely is the region where the model is giving high weight.
Okay.
Right. So do you think that it's we can consider that kind of a representation as a good example of interpretable machine learning? Or do you think that that's very heuristic still and it's not very convincing that the model will have a stable heat map across multiple iterations? So when I'm saying that, do you think Lime and Chap are more stable algorithms or they are still subjected to a lot of approximations?
Okay. So to touch on what a heat map does, so it's called GradCam probably because heat map is a name for a gradient map. So what is a gradient map mean? Is, let's say you have a relationship y is equal to wx. A gradient map means that when you change x by an infinitesimal amount, how much does y change, right? So typically what we are used to computing when model training is the parameters, the w, right? So when w changes a little, how much does y change? And that's how we train the model. But when explaining, we do the other kind of thing, that when you change the input by a little, how much does the output change? When you change the x by a little. These are called gradient maps or saliency maps or heat maps. There are many names for it. So what do they tell you? That when you're seeing an image, if you highlight a pixel, what are you changing? Not the parameters of the model, the input, the x, right? So when you highlight a particular, you trace a particular shape in your image, how much does that affect how you're steering? Right. So heat maps are as good as the approximation relationship that your original neural network has learned. So the key thing to remember here is, like I said earlier, the steering of a car is an extremely fine-grained control problem. And it is so fine-grained that the accurate way to steer a car may not actually be how humans think about it. So when you visualize the heat map, it may seem strange to you because it is just humans don't think at that micro level of perception, right? So explaining adverse phenomena probably requires thinking in terms of features that humans can understand that may have almost nothing to do with the features that actually direct the control of the car. If does that?
Yeah.
Yeah.
Yes. Okay, any other questions from the other projects? I can go along putting interpretability in almost all the projects that I'm aware of. Uh, but it's just a good thought. Like if you are interested, you can even write down point, like as a future efforts that in your projects, in your respective projects, if interpretable machine learning can play a key role. I think one particular pretty much I'm pretty much sure about Pranit and Siddesh and their team to be anyways working on Lime, so probably they would benefit if Lime is better than Chap, and they can actually put an argument along that line as well. So with this, I actually thank Kaushik for his presentation. If you have any questions, feel free to email him. His email is I'm putting in the chat, right? And one thing that I'm not really sure about interpretability is in the term of entity context graph or knowledge graphs, which I think Ranjan and his team are working on. So Ranjan, if you have any questions on the interpretability part of that problem, you can feel free to connect with Kaushik and see what points he have for your project if needed. And likewise, you can even always CC me in that interactions if that is applicable, is important to your project. Okay, so with this, we move on to the remaining few 15 minutes that we have for the class to cover up and just sync up the entire machine learning course that we just went through in this class. So let me share my screen, and this is about a very old study which we call which is termed as Hoeffdings inequality. So you can just remember and understand this terminology is called Hoeffdings inequality. So this is Hoeffdings inequality process, right? Now the reason I wanted to touch upon this point is first is it covers the entire circle of it circles the entire machine learning that we covered in this project, and it will tell you some few points that you should talk about or you should inquire or you should query yourself when you are developing machine learning models. So the first thing is that Hoeffding's inequality states a connection to learning. So there are two things: whether you want to ask that whether your model is actually learning model or it's just a verification model. So we'll talk about that in the few remaining time that we have. Okay, so this figure, as you can see in front of you, actually sums up the entire machine learning course. So as we started the course with talking about that we have an unknown target function which a model needs to learn. X is a data points, and we want to find or we want to learn the mapping from X to Y. That has already been a question in machine learning because X is coming up from some distribution we are not aware of, and we want to take we want a machine learning model to understand that unknown distribution and come up with the best approximation to the Y. And for how do I do that? We need a lot of training examples. We already know that in your projects, if you have done so far, you need a lot of training examples in order to learn this target function. Now, what this model does, what is your machine learning model A does, right? So the machine learning model A takes these training examples, look through his hypothesis set. When I say hypothesis set, means individual decision boundary. If I have one algorithm, one machine learning algorithm, it has one hypothesis set. If I change its hyperparameter, if I change its decision boundary, I have another learning algorithm. For instance, if I talk about k nearest neighbor, if it is a ball tree k nearest neighbor, I'm taking the terminologies which are there in scikit-learn. If it is a ball tree, then it is one k nearest neighbor algorithm. If it is a KD tree, it's another set of another machine learning algorithm, right? Like that, you have multiple series of decision boundaries that you can come up with. Those decision boundaries are your hypothesis set. So your learning algorithm is nothing but it's a framework that takes those hypothesis set, take this training example, and generate the final hypothesis. And I think this is what we even talked about when we were doing the Bayes optimality principle in the last class. The Bayes optimality principle is saying that the best learning algorithm is the one that works over all the good things that hypothesis sets are doing and ignoring all the bad things. That means you are coming up with a very idealistic learning algorithm that always takes, let's say there is a hypothesis set A that is or there's a, let's say there's a decision boundary 1, decision boundary 2, and decision boundary 3. All three of them together gives you an accuracy of 96%. That means you will always use those three decision boundaries to come up with a prediction and not one at all. So that's the Bayes optimality principle, and that actually connects the Hoeffdings point, saying that the learning algorithm is the one that takes this hypothesis set, all the decision boundaries, and your training examples, and come up with the best possible hypothesis that is can be a set of all the decision boundaries. But that's not a good thing in practice, because in the practice we need only one machine learning model to act in, or we want an ensemble or a combination of machine learning models that can learn in some pairs and something like that, right? So but the Hoeffdings point was well taken, that there's a possibility of developing this learning algorithm that takes a series of hypothesis set. But there's a challenge, and there's a reason why we only look for one machine learning model and not take a bunch of these hypothesis set as a machine learning model. Before we go into that point, there are certain things that we want to take into account. First, by assuming that the training samples came from a probability distribution P, we design our hypothesis. So this is the biggest assumption that you are taking in machine learning. Your machine learning algorithms are always created based on the first 2 points of the assumptions. Second, fixing the hypothesis and checking its error is verification and not learning. So that means if you run your model one time and it's just computing an error over some input data set, then you're just doing a verification and not learning. That means for the learning, you need to have a function that can continuously compute errors and keep on updating itself. So you need both the functions together. Otherwise, with only one function of error checking, it will always be a verification algorithm and it won't be learning. So always keep in mind there's a difference between verification, machine learning verification, and a machine learning perspective as such. So the task of the learning is to hence pick up the best hypothesis always. That means Bayes optimality principle is actually good. It's good to keep that in mind, but it's not deployable in practice. So because it's a verification algorithm and not a learning algorithm. So the Bayes optimal principle is a verification approach and not a learning approach. And for the learning approach, we always have a best hypothesis selected from a multiple set of hypotheses that we are working on. So your learning algorithm end up picking one set of hypotheses from multiple set of hypotheses. Okay, so what does this everything in this structure in this figure maps to? So what does this figure means that, and what does a learning means in a very simple sense? So if I want to ask, if anyone asks you what is a one short definition or explanation, mathematical explanation of a machine learning algorithm, is always that the machine learning algorithm is trying to minimize the error in the in sample and the out sample. Whereas in your training, your out sample is your validation set, in your in sample is your training set. The difference between the two is greater than, if this is greater than the threshold, then if the error is greater than a particular threshold, you keep on training it. If it is going beyond lower than a particular threshold, that's the point you stop. So the left side of this equation is pretty much the standard function that we all know of in a machine learning algorithm, right? E of in is the error that you're computing at the training on the training set, and the E out is the error that you're computing in your validation set. Now, what is this right term on the right hand side? So the right term, you only need to focus on the two component over there. That is a capital N over there, and the summation, and this epsilon E. Exponential point, you don't really need to point that. It just tells you that it's an exponential growth whenever there's an exponential function. But what is this epsilon square N? So it says that in a simple sense that if whatever approximation that you're putting over here, epsilon, right? When I say approximation, it means that if I'm saying that my error is is as long as it is greater than a particular threshold, keep training the model. As soon as it goes lower than the threshold, that's the point you stop, right? That's the definition of machine learning algorithm. Now, if you do that, this epsilon is nothing but an approximation. It's you're just putting this empirically. There's no justification. I think I raised these points in multiple project presentations in the class, where you say that we had a threshold, and I asked you the question why that threshold is there, right? What is the significance of the threshold? The reason is, if you have a threshold, you are approximating this left hand side, right? Now, if you are approximating this left hand side of this equation, there is a consequence on the number of samples that you need. If your epsilon e over here is, let's say, 0.6 and 0.7, probably you will need less number of capital N's over here. But if your epsilon is very, very low, let's say 0.001 or 0.0001, you need equivalently large number of capital N to in order to sufficiently say that your model has actually learned. So this equation is a very interesting equation in telling you that whether you, and you can actually put this equation into your algorithm and print out these results, saying that whenever the errors are coming up from the model, and if it is less than the particular threshold, how many samples more do I need for my training? So we know that cross validations by blindly says 30% and 70% splits, but there has to be some practical importance or significance of it. So that practical significance is this Hoeffdings point, saying that you do not need 30% 70% split always, but rather it's a justified way. There is a justified way of doing it that is dependent on the number of samples that you have in your data set, whether it's a training set or whether it's a test set. So what is Hoeffding's inequality translates into the concept which we didn't go into. We won't be going into details of this topic, but it is called probably approximate correct learning. That means whatever your model that you will be presenting in the future final project presentation, I will call them as probably approximately correct models. They are not the super correct models, but they are probably approximate correct models according to the Hoeffding's point. Because what you have exercised right now are within the confined bounds of certain probability epsilon and the set of samples that you have used. I remember some of the projects says that we have 1 million samples, we can't do it on that, we need a small subset of it. That's where your first approximation goes into the picture. That's approximation on the size of the samples, the number of samples that you need. And then again, approximation that you do is on the thresholds, right? And they actually defines your entire model behavior. So the Hoeffding's equation is actually in practice when we are doing a machine learning model building. So I wanted to take this equation and discuss with you at the end of the class, because now you guys already have a fairly good idea of machine learning, as well as in the theoretical aspect as well as the practical aspect of machine learning in your projects. Okay, so what does this entire equations translates to? So this is my translation, and pretty much you can actually keep that and mention it in your final projects as well, which is nothing but that you are actually minimizing, you're trying to minimize your errors between your train and your test, or train and your validation should be tending to zero, and it is dependent upon the number of hypotheses that you construct. When I say number of hypotheses, you are constructing the hypothesis when you are changing the learning rate, when you are changing the learning momentum, when you are changing the number of epochs, when you are changing the number of other parameters of your models, you are generating different hypothesis sets. So H with the straight lines on the side is the number count, the number of hypotheses that you are constructing, and that's multiplied by that equation is the ultimate bound on your errors, right? So if you look at this point, and if you assume this to be the structure that I showed in the class, that if this is a decision boundary, this is a decision boundary, and this is a decision boundary, then the surface enclosed between the three is the most justified and more idealistic scenario. And that's what this equation turns out to be. That whenever you are defining multiple errors, you have multiple hypotheses plane. The intersection of all of them is the best solution possible. And it will always be less than a particular threshold that you don't define it, because your definition is epsilon. This delta is a threshold defined by the experts in that particular domain, right? The data set from where you got it. So this entire equation is actually the entire process of machine learning, where on the left hand side is your training algorithm, on the middle side is the bound on what is the best possible accuracy or best number of models achievement that you can define. You can say that, Manas, that I am able to get 67% accuracy only because I have epsilon this and number of samples this. Probably by increasing the number of samples, keeping the epsilon constant, I might get a better accuracy as well, but that is beyond the constraint of my final project or something. So you have a justified reason by this behavior, and so is the epsilon. So now there are three questions that you guys have to think through, and I would appreciate this be a part of your final project as well. How do you know that the training set that you have taken in your data in your final projects has a good domain coverage? Does it really relates to the domain that you are working with? Is your model or is your final model robust? That means, can you say that it has a low generalizability error? So when I say low generalizability error, means that among different hypotheses and among different parameters that you have tested, this is the best possible model that you have come up with. So that's a low generalizability error. The last one is a low training error. Let me again go over the low generalizability error again. So low generalizability error means when you have bunch of models being practiced in your machine learning project, the model that performs the best across different configurations, different hypothesis set, different epsilon and n numbers, and still outperforms other models, is a model which has a low generalizability error, and it's the most robust model. The second point is a low training error, which is only about a model which has a low generalizability error will definitely have a low training error. But a model who has a low training error does not mean, I repeat, low training error does not mean low generalizability error. So your task is always to achieve the low generalizability error in your machine learning models. Okay, so with this, you always have key deductions and you always battle between confidence and complexity. The more complex your model is, the lower will be its confidence. That means when you have more number high complex models, you will have more complex hypotheses, and which means in order to satisfy all these complicated hypotheses, you need more samples, and that is the only fundamental reason coming from the pack learning that highlights deep learning. A deep learning is complex or complicated hypothesis building algorithms, and that's why they need more number of samples, and that is proven by this particular equation down the top, right? So that's what this pack learning is all about. So I would suggest to you all, if you have time and if you are really good in a stable position in your final projects, to try out the scikit.multiflow, which is a very interesting library to try out your Hoeffdings approach on your existing machine learning models. So you can try out how does Hoeffdings understand your machine learning model. As a good point to be added in your final project as a discussion of your efforts that you have done so far in the machine learning model building. With this, I conclude the machine learning course, and I didn't go into too details of certain topics. For instance, the probabilistic graphical models was one of the topic that I missed, and another topic that I kind of missed was bagging and boosting, but both of them are fairly easily implementable if you have thorough understanding of what we have covered, because they are derived models from what we have covered in this class. So with this, I hope all of you are in the good standing of your final project report and submissions. Regarding the midterm, I would be posting the grades on the weekend, and I would be also reaching out to the students independently regarding their midterm submissions as well. So thank you all
On the second
for
point,
attending to this
I
class.
don't
If
like
you have
the
any
words which you
questions,
kept in the
you can
book.
ask me in the
That's
chat.
listening
I'll
and
happy
ఎవరికి
to
తెలుసు
answer it right
ఎవరికి
now,
తెలుసు
even if it's
ఇవన్నీ
on
నేను చాలా
interpretable
హర్ట్ అయినా
machine learning.
హోలీ క్రాప్ అలా నేను కూడా దానికి హర్ట్ అయినా చాలా నేను మళ్ళీ నేను అట్లాంటి మాటలు మాట్లాడను ఇంకా నాకు రావు
Any questions?
Professor, is there any?
Yeah, I think everyone is muted, so if you can unmute, if you're about to say something.
Can you hear me, Professor?
And this thing that I talked about is already in the lecture page of the course web page. And if you want to go over there, I think it's the second lecture in that series of all the lectures that we covered in machine learning. So there is no page limit, Ranjan, for the report, but it all depends upon the clarity and consistency. So it's always like I will be focusing on the clarity of your problem and your report, in your report. So there's a possibility if someone has submitted a 4-page report, gets a good grade because he has explained it very thoroughly, compared to a 20-page report, which is full of verbosity or verbiage or a lot of content, which do not have any strong connections with your project. So it's always balance. It's good to balance between these two. Okay, with this, thank you all for the last, as we conclude our lectures on introduction to machine learning. And don't forget, if someone has a good camera, I would like you to bring it on the last day of the of the class, which is December 20. When we have the project presentations, I want to have a group photo with every one of you. Thank you all for attending to this class. Have a nice rest of the week. And thank you, Abhiram, for hosting the session.